Okay, so up next we have Francois joining us all the way from the Free State. Hoping that's okay. So thanks so much for coming out, and yeah, take it away.
Good afternoon. Okay, so I'm going to be looking at groundwater detectors, and although these instruments are called groundwater detectors, they don't really claim to detect groundwater. What they do claim is to record signal from which the subsurface geology can be derived, which is a claim that I'm not so sure about. And they've become popular not only with groundwater scientists, but also with geologists and engineers. So that's one of the reasons why I'll be looking at it. And the title says when easy becomes misleading. Well, I think one could change title to when easy becomes misleading and when cheap becomes enticing. Because if you look at these systems, you can buy them online for less than 10,000 Rand. So a local supplier provides the system for 32,000 Rand, the basic system, but you can buy them online for under 10,000 Rand. And yesterday, where is he? Has he left? He complained about geophysics not being able to pack in your backpack. You can pack at least 6 of those in your backpack when you travel. So, okay. So I did a bit of Googling, and I went to Google Scholar to see what publications we have on these groundwater detectors, and I found 130. That was at the end of June, or middle of June rather. But you can see the distribution of publications and how they are preferentially in the developing economies where people don't have access to the big budgets for research necessarily. And only 6 of those publications come from sort of the developed economies. You can also see that over the last 7, 8 years, so there's been a steady increase in the number of publications. So yes, the economic factor plays a big role in popularity of these systems. So what they claim to measure, they measure, well, the energy source is natural EM radiation from solar radiation and lightning strikes, and the assumption is that we've got plain EM waves traveling down the subsurface, down the Earth, and then the different frequency components of these EM waves travel to different distances, which allow you to measure at different depths. And they look at they assign the depth of investigation. They use the skin depth to find the depth of investigation. So in the end, initially they claim to be measuring resistivity, but they've sort of walked back from that nowadays. So you get some signal, some millivolt that is measured as a function of depth, and they can get a profile, and they say that these anomalies can be correlated with subsurface geological features. And if you have a number of these profiles, we can sort of get a 2D section of the subsurface. Yeah, so there are a lot of uncertainties still about what is being measured. But let's, oh yes, and also no one seems to know exactly what to call the system. So that from those 113 publications, these are the names that I found for the system. And lately they've sort of settled on telluric electric frequency selection method. But you'll see that audio magnetotellurics also feature a lot, the name. And as I described it just now, it seems to be based on the theory of magnetotellurics. So let's quickly do a very brief overview of the conventional magnetotelluric method, because I will need to show where their assumptions go wrong. So yes, they are right that the natural sources of EM radiation is it's a source of energy, and from solar radiation in the frequency range lower than 1 hertz, and above 1 hertz, it's lightning strikes that give us the energy that we can use to investigate the subsurface. And where these EM waves impinge on the subsurface, or let's say on the surface of the Earth, because they travel at a lower velocity in the Earth, the rays bend towards the normal. So that's why we can sort of assume that we've got plane waves traveling vertically down the subsurface. But also it's not wave behavior, it's more diffusion behavior, because these waves get attenuated. And the higher frequency components get attenuated much more rapidly than the lower frequencies. So that's why the skin depth for the high frequencies is smaller than the skin depth for the lower frequencies. But what's also important is to note that your skin depth is dependent on both the resistivity and the frequency. So it's the resistivity of the subsurface also determines just how deep you can, well, it determines how deep the EM wave penetrates into the medium. So in the conventional magnetotelluric method, we typically measure 2 orthogonal components of the electric field and 2 or 3 components of the magnetic field. And then it allows us to calculate apparent resistivities based on the orthogonal components of these electric and magnetic fields, and also phase differences between these different field components. And from these calculated apparent resistivities, we can get sounding curves as a function of frequency, which now, of course, related to depth, the higher frequencies corresponding to shallower depths of investigation. And then if you have where am I now? Who's going back over there? And if you have multiple sounding curves next to one another, you can compile a pseudo section of your observed apparent resistivities, and then you can, through inversion, create a model of the subsurface so that your calculated apparent resistivities resemble your observed apparent resistivities. So that's how, in a few slides, what the basics of the conventional magnetotelluric method. But now let's go back to the groundwater detectors and their assumptions. So first of all, the depth of investigation. So they assign, or they say the depth of investigation corresponds to the skin depth of that particular frequency component. So if you just look at the wave, to reach that position of the skin depth, it had to travel all the way from the surface of the Earth to that position. So all the material above the skin depth influences the response that you measure. So it makes no sense assigning frequency component to that particular depth corresponding to, well, let's say to assign your value that you record to that particular depth corresponding to the skin depth. So there are a number of problems with this assumption. As I said, the material above and even below the skin depth still have an influence on the signal that you record. And then this is a big issue. They assume some average resistivity for the subsurface to be able to convert the frequencies to depths. Whether you are working on a saturated clay environment or on hard rock granite outcrops, they assume the same apparent resistivity or same background resistivity. And I just showed this by a simple few examples of if you assume a certain resistivity for the background, what the effect would be on the skin depth. And you can see it makes a massive difference if you assume a different background resistivity. So this assumption of a homogeneous resistivity for the background makes no sense whatsoever. And of course, the subsurface is not homogeneous. So even that assumption in itself is doubtable. And then another thing is the skin depth does not correspond to the depth of investigation. Your depth of investigation is the depth from which you can, where your measurement is sensitive to changes in the subsurface properties. Skin depth is just a measure of how deep a EM wave can penetrate into a medium, but it doesn't tell you how much or whether you can gaining information from the subsurface at that depth. And then another assumption is that you can assign the signal that you record to positions vertically below you. But in fact, the signal that you measure at surface is sensitive to a bulk volume of the subsurface. So materials laterally displaced from you affect the measurements that you take. So you can see there are sort of 3 assumptions that they have made now. They've assumed that you have a homogeneous half space with a specific resistivity. They assume that you can assign your signal laterally to where you are taking your measurements between your electrodes, and they assume that you can also assign your measurement to a specific depth position. And those of you who've done ERT surveys, that should sound familiar because that's how we construct pseudo-sections. You assume a background, or you assume you're dealing with a homogeneous half space, and you assume that your lateral position is determined by the positions of your electrodes, and you assume that you can assign the signal that you record to a specific depth, a pseudo depth, based on how far your electrodes are separated from one another. So at best, these 2D sections that we get from these groundwater detectors are pseudo sections. And we don't normally interpret pseudo sections because pseudo sections give a very distorted view of the subsurface. To illustrate this, I just took look at a small conductive zone in the subsurface, and we did forward modeling for different electrode arrays. And you can see that the pseudo sections don't resemble your input model at all. Only once you've submitted your pseudo sections to the process of inversion do you get models that give a fair representation of your input model. They're not perfect by any means, but you can at least say that, well, I can identify the conductive zone in the subsurface. So we went to a site near Loxton where we had a nice prominent dolerite dike and also some fault zones. I thought, well, this will be a good site to test the system. So we recorded magnetic, EM, and I blocked out the name. I don't want to get sued. Groundwater detector surveys across perpendicularly across both the dike and one of those fault zones. And you can see the dike, it's an outcropping dolerite dike, about 4 meters thick. And then all there we have the upturned bedding or the sedimentary layers in the fault zones. And here are the results. The magnetic survey, almost a textbook example of a magnetic anomaly. And the EM survey also showed the higher resistivity, lower conductivity of the dike well. And you can see the ERT survey also showed the dike pretty well. And then when I initially did the survey with the water detector, groundwater detector, I got this anomaly. I thought, oh, wow, it seems to work. It seems like this, perhaps I was wrong being so skeptical. Then I adjusted the maximum depth of investigation, and I can see you get 3 totally different models depending on what you select for your maximum depth of investigation. What's more is that you can see that these anomalies are the same anomaly, just stretched or vertically or squashed vertically. So, well, if you change your depth of investigation and you get a completely different model, that should set off all sorts of alarm bells. And there's the survey across the fault zone, small magnetic anomaly, small EM anomaly, and also you can see there's a lateral change corresponding to changes in the subsurface resistivities and a zone of greater conductivity. And for the groundwater detector, similar to the previous slides, we get three totally different models of the subsurface depending on what we select as our maximum depth of investigation. But again, these anomalies are the same anomaly, just stretched vertically or compressed vertically. And to show that I actually overlaid the anomalies, they're the same anomaly. And then another thing that's, when you look at the published works on these groundwater detectors, you often see these vertical anomalies, and they are often sold as being fractures or faults running straight through. And and you never see, well, you hardly, I haven't ever seen dipping features. They're always horizontal features and these vertical faults running through them. And what we think is happening is that whatever you measure at surface sort of gets smeared down. So if you have 2 electrodes and they might be, let's say, in a puddle of mud, and there's sort of a short circuit between them, those low voltages that you measure at surface, they're just in some way, the way they process the data, those low values get smeared right through these sections. So they claim to be measuring AC signals, but we're not so sure about that. And that's the thing, throughout this meeting, we've been speaking about how engineers like to quantify the uncertainties. Over here, we don't even know what the uncertainties are. There's just no way to really put any certainty on what you are measuring. And here's just another example. It's not the best example of a survey I did on campus of University of the Free State. And there's a site of a lot of noise, surface noise and subsurface wiring and pipes and all that. But still, I sort of tried to plot them at the same vertical scale. And you can see for the ERT model, there's just no corresponding variation in whatever we are measuring with the groundwater detector. And the only sort of agreement I can see is this zone of high resistivity that might correlate with what we see there. Again, it appears that what you measure in the near surface is somehow transposed to greater depths, and somewhere it is a bit strange. So, yeah, in conclusion, we think these systems are based on flawed assumptions, and we don't really think that you can get information on the subsurface that's usable or that is of any value. And so more recently, well, a couple of years ago, this Yang did some model studies, and he suggested that we are basically measuring what we also said, the response from the near surface materials. And he suggested we should call it the static shift method. Static shifting metallurgics is basically you're compensating for the presence of these conductivity changes in the near surface. So yes, our results cast further doubt on whether these systems can actually give you measurements that are of value to engineers and geological scientists. Thank you.
Thanks, Francois. Jeff?
I applaud your sense of technical purity, but you're fighting against the market here. Telluric voltage methods do work, and they do indicate at least the horizontal, the X and Y positions of changes in resistivity. I'd agree with you on the rather improper assumptions based upon depth, but the proof of the pudding is in the eating. A friend of mine, and probably yours, imports these groundwater detectors from China. And so far, he tells me he sold over 120 of these at great profits. And the main clients have been drillers. And if you go to something like the websites of Eyewitness News or News 24, you will see that a local company has started advertising extensively on their hydrological services using exactly this kind of groundwater detector. And they can't be taken to court because any kind of electrode system over at least an area of water concentration is going to give you a pseudo-resistivity low. So even though the technique is totally improper, they cannot be taken to a court of law in terms of the fact that they're advertising a service which they don't have. So the only thing you can draw from that is that the public is not scientifically minded. So the only way you get your much more expensive techniques rewarded by future input and projects is to advertise. So I would definitely disagree that the technique has been mislabeled as a cure-all, but the drillers are using it as an assist. Rather than using a divining rod or a metal coat hanger, they're using one of these groundwater detectors, which is measuring the telluric voltage.
Well, that's what they claim to be measuring. I'm not so sure that it is what they are measuring. Like I said, I think that for example, the dolerite dike, the electrodes were physically installed in the dike. So you'd expect a system that measures potential differences to respond to that. So I agree with what that Yang said, that the system at present measures the very near surface response to the very near surface material, and then that's somehow that response gets smeared downwards in depth. So I don't really even think that this system really measures telluric effect. When I did AMT survey recently, also with a mutual friend of ours, in the early mornings, we don't really get good MT signal at all. This system works perfectly in the morning. So I don't know what we are measuring.
Okay, I guess we could go on talking about various anecdotes, but I would leave it then.
Okay.
Have you done any mapping with this and
No.
produced a 2D sort of plan view of what that data might look like?
No, I haven't.
Because it'd be interesting to see, irrespective of the depth projection of the responses, whether there's correlation to lateral variation in geology.
Yes, that would be a good thing to do. Then you can see whether it is, in fact, the surface response that you're getting.
Yeah. And then have you taken multiple measurements over an extended period of time in the same location? If it is time related.
Well, in this particular case, I did repeated surveys and I got exactly the same results, but I know that other people have returned to the same site couple of days, couple of months later and got completely different results. So even there's uncertainty about just how repeatable the results are. So the whole system to me is a big black box at the moment, and there's no real documentation provided by the suppliers. So it's difficult to judge the scientific validity or soundness of the method.
Francois, I just wanted to ask, are you able to get the data off of the instrument now? So you actually have numbers? Okay.
Yes.
Yeah, because for a while you just had pictures.
Yeah, you can get the numbers. What they mean, you don't know, but you can get them.
Yeah. Maybe just to inject some energy into the graveyard session. The shack process that Ray described earlier, to cut a long story short, one of the workshops is to pull in proponents not involved in the project to come and put forward theories, etc. And a fellow who should remain unnamed did a presentation on what he was terming pseudo faults, and he went through the whole thing. And afterwards, there was an American guy in the audience, and he asked the question. He said, "Can we assume that pseudo faults are identified by pseudo geologists?" So maybe you're talking about pseudo geophysicists.
Okay. Oh, Jeff?
Just a closing word from my closing word, not yours. Telluric works. In the early 70s at JCI, we built a telluric device to map things like the thickness of Karoo, and it worked. And we only discontinued that because at that stage we suddenly discovered the effectiveness of seismic reflection mapping. But telluric voltage prospecting is also mentioned by Keller of Keller and Friction fame back in the 60s, I think, and probably continuing editions. Your turn now.
Yes. So just to add, Francois, tellurics works. It's a real method because that's what we rely on. The argument here is this: we don't think this is tellurics.
Exactly.
So we're not going against the telluric method. It's the system is not clear and is not repeatable, and we don't think it's tellurics. So we're not saying tellurics is wrong. We think that this system is. Just the end there. Thanks.